welcome to Web Building, where we bring insights out of Web3 builders. This podcast is made possible by our sponsor Untill Labs. Untill Labs is a Web3 developer community dedicated to push the boundaries of crypto space by supporting the innovation and success of open source projects. Hello, listeners of Web Building Podcast. I'm your host, Franci. So today we have Dr.Cathie here. She's the ZKML research from the Privacy and Scaling Exploration team of the Ethereum Foundation. So in this episode, we are gonna focus on the implementation of zero-knowledge proof, especially the proving side. So you may hear some terms like proving systems, proving schemes, writing circles, etc., etc. If you have no idea about these things at all, don't worry, that's why we have Dr. Cathie here. So, Cathie, could you introduce yourself and tell us your personal background or crypto experiences or anything you'd like to let us know?
Well, thank you for having me. I am actually a ZKML, so zero knowledge machine learning researcher at PSE, Privacy and Scaling Explorations, which is like a team under Ethereum Foundation. Even though I work in ZK, my background is actually not in cryptography. For the longest time, I have been in data science, in machine learning engineer. I got into ZK because of an education program that I did call Zero Knowledge University. So that is actually something that I have done as an open source program that I've worked with another project before. And we aim to bring like ZK developers, we aim to bring Web3 developers on board to ZK. And at that time, actually, I knew nothing about ZK. So I kind of had to self-study everything and wrote a course about it. So that's kind of like my background and my experience. But I was really interested into how to get like machine learning into ZK, and that's kind of what I did for personal projects, and eventually I got into this whole like field of research.
Okay, thank you again. It's really great to have you here, Cathie. So we know that in the past few months, a rising star called Nova kind of got everyone's attention, especially those cryptographers and builders working on ZK projects. And honestly, I'm still trying to understand what's going on. And thankfully, I have you here who can explain these complicated things to a more general public. So, what does this Nova thing mean for crypto or the whole industry? Could you just give us some very straightforward implication it might bring to? Let us go through some wow moments.
I guess since we're looking at probably a more general crypto audience, maybe I could use an example as an example, which is like CK rollup or CKL2 that I think a lot of us have already heard about. So I'm not saying that any project actually currently does it, but imagine if we could apply the Nova technique on some CK rollup. So what Nova is actually what we call a folding scheme. So essentially it folds the same computation or operation, like something that you do over and over and over repeatedly, and it folds it into what we call a proof size of 0.1. Okay, so 0.1 meaning like it doesn't scale with however many we have, right? So we're saying that if we do 10 times, if we do 100 times, if we do 1,000 times of the same thing, the outcome is going to be around the same size. This is what we're talking about when we say like folding scheme, right? So you can imagine that one possible use would be something like CK rollup, where we are trying to fold the blocks in a layer 2. So typically it scales with how many ever blocks we want to prove, right? So currently what we do is we batch the different blocks together and we try to like aggregate the proofs and then try to like submit the proof to Ethereum. But let's say if we have something like a Nova or folding scheme, what could possibly happen is that it doesn't matter whether we want to prove 10 blocks at a time or 100 blocks at a time, the cost will be roughly the same. So that's kind of like what, in essence, what Nova could do or could be.
Okay, so I catch the keyword folding. So I don't really understand the underground technique, but literally I think it's just like folding something. It's just like you can save much energy and cost. Am I right?
Yes, in a sense. Actually, that might bring us also to talk about the prover and verifier a little bit. Because when we are talking about folding, we are actually talking about saving the cost of verifying the proof. So maybe we should get into prover and verifier before we continue to explain folding.
Okay, thanks for leading. So in general, so what's the sketch behind the prover and verifier going for backward and forwards to complete this complicated process? Just like as you say, verifying the proof, something like that.
Right. So the process you just mentioned, like going backward and forward, is called a interactive ZKP, so interactive zero knowledge proof. And that is usually what, when you first hear about zero knowledge, that's the story or the examples you hear about, right? So one of the very typical examples you might have heard of is people saying that, let's say I'm colorblind, okay? So Cathie is colorblind, and let's say you have two balls that is one red and one green, and you want to tell me, you want to convince me that they are two different colors, right? So to me, I can't tell, but actually, if you, every time if you kind of, if you give the two balls to me, right, and I switch them, you will be able to, because you're not colorblind, you are able to tell me which ball is which. And eventually, if we try many times this process, then I know you're not guessing this purely out of luck. I know that you truly know the two colors of the balls. That's why you can tell me whether I have switched or I have not switched, right? Which one is on my left hand, which one is on my right hand, etc. So this is an interactive process, right? Because it's about probability, right? One time could be a guess, two times could be two guesses, right? You can be lucky. But if I do that 100 times, then there's no way that it's out of luck. And that is what we usually call like an interactive proof. So that will involve the prover and the verifier going backwards. So the prover will be you who try to prove to me that the two balls are different, whereas the verifier will be me, right? Because only I know whether I've switched like the position of the balls. So that's the kind of when we say going backward and forward, and that's an interactive proof. However, when we talk about in, let's say in all the blockchain applications that we have been talking about, rarely ever are we doing interactive proofs. Usually we are doing what's called a non-interactive ZKP. Okay, so non-interactive zero knowledge proof, whereas this proof generation and verifying process only happen once. Okay, so you have a prover that generates some mathematical statement, and then you have a verifier that verifies this mathematical statement. And the verifier, when we're talking about a blockchain applications, is usually a smart contract. It's a smart contract that already is all written on chain that is able to verify these mathematics. So that's kind of like, I guess, the process. So for example, I can give an example. I think a lot of us have heard of, say, Tornado Cash, right? So yes, the verifier and the prover process basically works like when you deposit some money into Tornado Cash, the prover actually sends you this receipt that you can later submit to the verifier to get your money back. Right. So that's a one-time process, and that's a non-interactive ZK proof.
Okay, so the mathematics you mentioned that submit to the verifier contract is like a black box for me.
Right. I think it is a black box to a lot of people. And as I mentioned, I'm not a cryptographer. So actually, I wouldn't say I fully understand the mathematics either. But it's basically, if I have to put it in one kind of simple way to put it, it's like it's like answering a mathematical quest or a mathematical question. However, so the verifier is like, I can verify the answer to a mathematical question. And the prover is literally the only person or the only machine in this world that can answer this question, right? And only with the correct inputs, right? So this is a guarantee. That's why it's called proof, right? So only the prover has the capability of generating this correct answer that will make the verifier say that, oh, this answer is true. Everyone who tried to fake an answer or try to put in any other random answer would lead the verifier to say false. So this is kind of, I guess, what we're a very high level overview. Of course,
Yes.
behind that, there's a lot of different mathematics that goes in. So that's why you will hear about different proving scheme or different proving system. Some of the more, I guess, famous one would be, we all started with growth 16, which is something that's based on elliptic curves. Again, I know these terms are all very foreign, but in essence, all these mathematics is just trying to guarantee that it's very hard to guess this answer to this, to guess this correct answer to this verifier. All these mathematics is just trying to guarantee that only the prover with the correct input is able to generate something that the verifier will accept.
Okay. So the prover is self-proving. Can I say that?
Typically, the prover, well, depends on the application. So the prover might take in some inputs as well, right? Some
Okay.
user-generated inputs. Yeah.
Okay, that makes sense. So I still want to know that, is there a program to do this thing for the prover? So we all say decentralizing the prover. So it sounds like everyone can do the proving. So it's really high level for me. So I just want to know, for the node outside of this network, just they want to get into this process. So how do they run this kind of prover?
Right. So when we say a prover or decentralized prover, we're talking about a specific application, right? So for a specific application, the prover is actually a computer program, just like any other computer program that we write. Of course, the logic inside is based on the mathematics, it's based on ZKP, but after all, it's just a program. And this computer program could be in all different sort of language. It could be in TypeScript, could be in Rust. So that doesn't really matter. It's only that this program, if, as I said, because it's basically, it already satisfies guarantee, right? So no matter who hosts this program, no one should be able to forge a proof. So when we say to decentralize the prover, it's basically saying that what if we have many copies of this computer program that is distributed among different machines so that everyone can essentially be submitting this proof, right? So I guess it's also sidetracked a little bit, but also when we talk about decentralized prover, I think it's also a more of an incentive thing. So in technicality, it's just about really copying the program to another server or even like my computer so that you can do it yourself as well, right? But let's say for example, for a CK rollup, right? Why would suddenly a person at home would want to do it? So that it's also a little bit about incentive. Sorry for sidetracking, but yeah. But basically, the prover is a computer program that you can run on any powerful machine.
Okay. We haven't talked about proving systems. Can you just give us a brief explanation about this?
So proving system or proving schemes relies on basically it's kind of like what type of mathematics is used to generate the proof. So as I was saying, like the example I gave just now, growth 16, which is something that probably a lot of people when they start out in ZKP they've heard of. So growth 16 is based on some mathematics called elliptic curves, and it's a proving system that is based on a constraint system called R1CS. So that's kind of like how everyone started with, and it's largely associated with the language circum. And the reason being, like, for a specific type of mathematics, the type of proofs you write will also be different. Okay, so we started with something like circum where we can only write what's called a arithmetic circuit. Okay, so arithmetic circuit just means that all you can do in this program is plus and multiply. Okay, so that's very different from all the computer programs that we have normally done, right? So plus and multiply, and you can, for each line, you can think of, for each line of constraint or code, you can only go up to quadratic, right? So quadratic means you can only have something multiplied by something, like A multiplied by B plus C. So that's all you can write in the typical like circum scenario. And that is a lot of constraints, right? That is very different from usually what we do. And that's kind of like, but we all started there. Then we moved on to something that is a little bit more flexible, called, now it's largely called plonkish systems. But it started with plonk, but then we now have many variations of plonk. But largely it's called plonkish systems, where it works on custom gates. Custom gates meaning that now we have more than just plus and multiply. Okay, we can basically self-define some operations that will basically make our life easier, right? Because like imagine if you need to write a computer program that is just plus and multiply, that will be very inconvenient. But if we can write something with custom gates, that will be more flexible. And then we also move on to something that also is unique. Well, right now it's unique to plonkish system, is called lookup. So lookup is basically saying that, oh, if we can't do certain operation in CK, why don't we just write up all the possible outputs, right? So we have this big table where we write down all the possible inputs and all the possible outputs, and we just do a lookup. So it's literally meaning of the verb lookup. So that also brings a lot of flexibility, right? So I think, so these are like currently the more popular proving systems. So you can see why maybe a lot of people have moved from, like, let's say something like growth 16 into plonkish because of the flexibility. But I think with Nova, right, because this is also one thing that we want to highlight today, it also kind of moves everyone back to the R1CS systems, because Nova doesn't work on plonkish system. Nova works on R1CS. So we are kind of going back and see, oh, actually, because of this Nova folding magic, now a lot of people is revisiting previous popular proving systems as well. So so different proving system, basically they rely on different mathematics. They support different operations. So there are different like limitations to it.
Okay, so it's just like what application you want to build, so you can, based on that application, and choose some suitable proving systems, right?
Yeah, actually, yes. Because, for example, so let's take growth 16 and plonkish system as an example again. They also have different trade-offs, not just like that's beyond just the operations. So, for example, if you use growth 16 for your application, you need to create a trusted setup ceremony that is unique to your application itself. Okay, so what we call is called a circuit-specific trusted setup. A trusted setup is, well, okay, so right now a lot of proving system needs a trusted setup, Trusted setup is basically saying that we have a lot of people contributing some randomness into the system, right? So this randomness could be like a number or it could be a word, right? So for example, if I contribute, I will probably say something like Ethereum is the best, right? But I shouldn't know this, and I'll just add this randomness into the system. So this randomness is kind of what guarantees the ZK proof is hard to break. Okay, so and then depends on these proving systems, there's actually different requirement of this trusted setup. So Group 16 it requires what we call a circuit-specific trusted setup, or if you want to think about it, it's application-specific trusted setup. So meaning every time that I change even a little bit of my code, or if I write a new application, I have to do this trusted setup process all over again. But for example, if I use a plonkish system, I only need to do something called a universal trusted setup. And that's something that a lot of people have already done already. For example, Polygon Hermes has some trusted setup like files that we can download that everyone can use, right? Because they already have like hundreds of people contributing to their trusted setup, and we can just borrow that because for plonkish system is universal.
Okay.
So like one trade-off, right? So you can imagine if I write an application and I have to do my trusted setup, it's like, but at the same time, actually for Group 16, sometimes actually cheaper to verify. Cheaper, I'm saying that like assuming the, assuming the verifier is on the blockchain, right? That it takes some gas fee to verify. So there's actually a lot of these trade-offs.
So does this techniques of these schemes fast? And just feel, how do I say, feel sorry for other builders. They have to know about this to choose the right one?
I would say yes, in general, although we are trying to abstract that away. So as I said, normally or previously, usually the language, it's tied to the proving system. Okay, so for example, Circom originally is tied to Group 16. However, it also supports plonk now. And also I think something called flonk, flonk, yeah. So, and then, for example, I think Noah, so Noah from Aztec used to support plonk. And then now it also supports what's called ultra plonk. And I think they're also thinking of like building like a Halo 2 backend. So it used to be that the language and the proving system, it's like a pair, right? So by choosing the language, you choose also the proving system, but it's being more and more abstracted away. So eventually, what we're trying to do is we're trying to abstract away which proving systems you're used, and also to decouple it with the language that it's tied to. So hopefully in the near future, developers would just be able to write the program, like write it in one of the ZK language, and then maybe choose the proving system like later. Yeah, but still, like when you're trying to deploy, you still need to choose it, right? And that's the same with any production grade, I guess, application, even in Web 2, right? You need to choose which server, you need to choose which architecture. And I feel like choosing which proving system is just one of those things where you are choosing the infrastructure that is the most suitable for your application.
Okay, so you just walked us through how the prover and verifier coming together to complete this process and told us the underground techniques like proving systems, circular languages behind all this process. Alright, so now we are gonna move on to the next topic. So I realized that some blockchain maximalists, they just want to make use of the succinctness and completeness of ZKP, while in practice they still have some troublesome challenges. By this I mean maybe when doing the proving job, because a lot of large of computational resources, And on the verifying side, still we have some intractable problems. So Kathy, could you extend this for us?
Yeah, so first of all, I think at least out of the research that I've read before, it's almost always a trade-off between proving cost and verifying cost. So by cost, we mean either time or in terms of blockchain, it might be the gas fee, right? So proving is off-chain and verifying is typically on-chain. So at least for now, because we're talking about blockchain, usually we try to make the verifying side as cheap as possible. So, and that the trade-off means that usually the proving will become very expensive. By expensive, I mean it takes a lot of time or a lot of memory. So that's what we mean by proving is expensive. So I think right now, that's why you don't hear about proving on your laptop, right? You always hear about proving it's on a server, on a very powerful server, actually, whereas we can verify on the blockchain, right? So I think for the proving side, well, at least because I work in, again, zero knowledge machine learning, so I only know kind of the benchmarking from there. But what we are essentially like estimating is that like to do the same logic in regular program, right? Like let's say for machine learning, it will be Python, right? So if we do the same logic in Python versus if we try to run the same logic in ZKP, the operation is currently 1,000 times more expensive. But by 1,000 times, I mean if your, let's say if your machine learning model typically runs in a machine that only needs gigabytes of RAM, right, which is like a laptop or a powerful GPU. Now, if you want to do that same thing in ZK, it takes around terabytes of RAM. I think you probably haven't heard of any machine that is available to retail, right, with terabytes of RAM. So we're talking about probably something that is on a cloud server. So I think that's one of the biggest challenge on the proving side is how do we make that cheaper? And of course, there is a lot of ways of making that cheaper. One is hardware, which I am not an expert of. So I will not talk too much about that, but just to know that there are a lot of companies and projects trying to accelerate ZKP from the hardware point of view, right? So that includes something like doing ZKP in GPU or doing it in FPGA. So there's a lot of technique trying to improve it in a hardware side. Meanwhile, there's also what we try to improve the proving side from the software side. And that's something like what Nova comes in, right? So, Nova actually doesn't help with the proving side. So we will go into that when we go to the verifying side. But the proving side, we're also trying to do a lot of software changes, right? So that also, so from the software perspective, it depends on a lot of things. It depends on the backend, right? Which proving system. So going back to which proving system we use, that affects also the proving time. But also even just how we write our program more efficiently. How do we have a logic that translate our regular operation into ZKP more efficiently, which will also help with the proving side. So that is like what we are trying to do, or like to tackle the challenge on the proving side. On the verifying side, it's a little bit of a different story. So verifying cost has a lot of different dimensions. So as I said, one thing is the trade-off between verifying and proving. And usually we are already trying to do all the heavy lifting in proving to save costs on the verifying, because verifying cost means gas fee, and we do not want to make that gas fee expensive.
Yes.
But there's also other things that affects like verifying costs. For example, how much data are we outputting from this ZKP? Again, using machine learning as an example. If I want to for example, do stable diffusion stable diffusion, the generative art in ZK, and I want to put the whole image right to the verifier to verify, of course, that will be very expensive. Is there any other way, for example, like hashing the image that will make verifying cheaper? So that's also, again, like how you write the program matters. But that also leads to other problems like, okay, if I hash it, then I have to make the data available elsewhere, right? So it's a data availability problem. So if there's a lot of trade-off in your program design. And but however, going back to our star today, which is Nova, Nova actually mainly help with the verifying side, right? So Nova is basically saying that if we're trying to prove the same thing over and over again, now the verification cost will actually be the same or about the same as if we're just trying to prove it once, right? So that means that we're saving a lot of things. We're saving a lot of costs if we're trying to verify the proof. And so I already used the L2 example, but we can also imagine that for AI or machine learning as well. Like, for example, typically when we say we do a machine learning model, we don't apply it to one data point, right? We apply the model to many, many data points to get something like an accuracy, right? And you can think of it, if we do this individually, the verifying side will be very expensive. But with something like Nova, because we're able to fold them into one, then now we are able to verify this proof much, much cheaper. So that's also something that we're kind of like tackling on the verifying side.
Okay, but is that also a chance that Nova can do is that it is lowering the barrier to entry in terms of computation resources?
Yes, definitely. So yeah, one thing that I didn't mention is also Nova could help with proving side by parallelizing the computation, right? So essentially, if you are able to break your computation into many small building blocks and able to prove them individually, parallelizably, it could also help with the kind of the cost, right? So instead of it needing like a large memory, now you can do it in your laptop, but perhaps it will take more time. Or you can maybe do it with 100 laptops, right? So you can decentralize this thing as well. What if I have 100 laptops that are each able to prove a small building block, right? Then I can also do that, and if essentially like remove the need of having to have a large machine to do that. But at least like it will save, like, I guess, computational intensity, but it wouldn't really save time, at least for now.
So is that so Nova is Nova the most advanced technique in the proving systems?
So there are, even after Nova, there's a lot of extension on the Nova end. So something like hypernova, which you can also then like fold arbitrary computation. Like the computation doesn't have to be all the same, right? Because Nova means that when we talk about Nova, it means that all the blocks, you can think of all the things that you have to prove, like all the individual proof are exactly the same program.
Okay.
Whereas now we have hypernova, which is aimed to do to fold arbitrary computation. So different things can be folded together. There's also something called cyclefold, which we don't necessarily need to do the intermediate computation as much as Nova. And that's on the Nova side. But even on the plonkish side, so Nova is, as I mentioned, more on the CCS side. But on the plonkish side, there's also a lot of different new kind of advancement. Especially, I think something that is released from A16Z a couple of weeks ago called LASSO, LASSO. So that's probably like the latest research on how to improve kind of like lookup performance. So that's on the plonkish side. So I would say like for like, it's like how Plonk become plonkish, Nova has also become like a novaish ecosystem where there's a lot of research around that.
Well, I just feel like that everything is going so fast. Feel sorry again for the builders. So that leads to our last topic. So I think lastly we will have a casual talk about ZK developers or ZK builders onboarding. So as a branch of cryptography, zero knowledge was seen as a boon-based by so many blockchain builders. So that somehow leads to a situation. ZK research is far ahead of ZK applications. So by this, I mean, I think there are many advanced reports or papers on this field, while little real ZKP projects came up and developers neither. So how do you think of this? Firstly, do you agree with my point of view? And I just want to know, is there a gap between theory and implementation? So, and the moon math theory is the most obstacle to deal with. Can you give us some your experience getting into building the ZKP stuff?
Right. So, as I said, well, I personally don't fully understand the root math.
Okay.
And back to the open source course that I did, the Zero Knowledge University, I also used to tell our students that, like, just from the first class, I used to tell our students that we're not talking about the math. And for 8 weeks, we teach them to build a CK application without any, well, not without any, okay, without the hard mathematics that goes into it. Okay, so I think it's totally possible to not understand the math or, well, not fully understand the math and just go ahead to build. And I think the moon math fear also comes with how well, I wouldn't say for all, but at least for I'm based in Hong Kong, and at least I know that in Hong Kong, the education system has told us that we need to understand all the theory first, right? So
wow,
that's why I know a lot of people spend
that
time, right,
resonates
reading
with
books.
me.
Right? Like you need to
Yeah.
understand every single thing behind it first until you can use it. And I don't think that is true for a CK application. Because to be honest, if you understand everything before you start building, you might not end up a developer. You might just end up being a CK researcher, right? So I think there's a lot of room with just people building projects without understanding the math. For example, I know that like you can, well, there's different level of abstraction among the different languages. So by abstraction, I mean like how far away you are from the moon math, right? So let's say from the far end of the spectrum, we have something called a ZKVM, not CKEVM, ZKVM, right? Whereas they basically do the CK behind the scene. And you write the program as it is, right? So that an example being RISC-0. RISC-0 has a ZKVM in Rust, and the program you write is basically just Rust. There's no circuit. You just write the program as you will. So that's like the most far away from abstraction. And then we also have something like Noir, which is like in between Rust and their own circuit language. And then we also have something that is like Circom, which is like circuit. And we also have on the very far end, like something like Halo 2, where you absolutely need to understand, Plonk in order to write Halo 2. Right? So there's a far spectrum. And of course, like any programming language, we always know that the most high level is usually the less like computational efficient, unfortunately, right? So if you understand the moon math and if you want to write in Halo 2, good for you. But I think there's also a lot of different choices, that you can write a program and not fully understand the moon math, and the back end or the compiler will help you turn that into ZK. So yeah, I think that's totally possible.
But my question, I still have a question, is that do you think besides the ZK developers onboarding, is there a gap between theory and the implementation? Because I think, how do you think that maybe there's still so little ZK app come up? Is that just because the innovation, or because there are so little ZK builders built on it?
I would say a lot of people are fascinated by ZKP, and I've heard a lot of developers who want to build a ZK application. I would say, however, there still need to be a high level understanding of ZKP, because typically people would think of ZK as this magic that would just suddenly give us privacy, right? And so a lot of the time people will think that, oh, I can build this application, or I can build that application, but that actually doesn't have anything to do with ZKP. It's not really compatible with the limitation, right? So just because it's ZKP, just because we can do privacy with it, doesn't mean that every single privacy application would work. So that's, I think, one thing is we still need to have better education and like high level understanding of ZKP to everyone, so that they at least know what could be built to it. And I think another thing is to understand that this is really just a tool that is available to you that could be part of your project, or if it doesn't need to be, it doesn't need to be. I don't think we need to push like ZK applications as hard. Of course, we have a lot of ZK applications that is like, for example, in PSE, we have a lot of grantees building on ZK applications. So those are really kind of like the applications that we want to see built or in demand. But like, there is also no need like to force it in the way that like if an application doesn't require ZK, it's okay to not use ZK. At least that's like my personal take. But that being said, I think, because of the whole kind of moon math fear, I think people tend less to just even try to get to know it a little bit. And I think as we try to get to know it a little bit more, you will figure out that you actually don't need to understand all the moon math in order to do this. And so I just hope that there are like more developers who would like at least look into it, and then we can talk about whether it makes sense to use ZK for the application or so on and so forth.
Okay, thanks. You're encouraging. So now we are going back to the thing you are mainly doing. We know Dr. Cathie is now focusing on ZKML with proof recursion. So currently you are using Nova implemented on ZKML. So could you introduce some of your research and explain how recursion can use in ZKML?
So let's start with what ZKML is, or summarizing what ZKML is. So ZKML is basically trying to put machine learning model into its ZK counterpart. So like having machine learning model runs in ZK. And so that you can imagine it to be very expensive, because even without ZK, typically machine learning model already requires a server to run or a GPU to run. And as I mentioned, it's at least 1,000 times more expensive if we want to do it in ZK, right? So that's going to be super duper expensive. However, we can also make use of something in machine learning, which is machine learning has a lot of repeated, very structured operations, right? So by that, I mean, like, for example, if we have a convolutional neural network, which is like just applying matrix multiplication over and over again, right? These matrix multiplications are the same operation, right? So if you want to do all of them in a full program separately, of course, it will be very expensive. But what if we can do proof recursion over them, right? If we can do proof recursion over them, then essentially what we can do is, apply Nova or apply any other proof recursion technique. And that could shrink the number of, that could shrink our proof size by a lot. And that could also parallelize the proof generation process. Another, I guess, easier to understand example is before convolutional neural network get very popular, there's a thing called recurrent neural network. So recurrent neural network basically means it's a chained, like each building block is like one operation. and it's chained so that it can do something like time series forecasting. So these are like recurrent, meaning that the input of one block is put into the next block and is put to the next block, right? And this is exactly the structure that you will hope for in some of these proof recursion techniques like NOVA. So you can also do very complicated, like for example, time series prediction in proof recursion and have a very small kind of like proof overhead. So as long as we can like make use of these like very repeated operations or structure in machine learning, there's actually a lot of things that like proof recursion can bring the prover cost or the verifier cost down.
It's just like that the machine learning has the demand of intensive computing, and the structure of proof recursion just fit in there, right?
Yes, exactly.
Okay, so I think today's talk is about time. So thank you, Cathie, and see you until next time.
Yeah, thank you for having me. Thanks.
Bye bye.
Bye.